Hello, hello students. Yes. So today we are going to deal the topic chemical kinetics, right? So what do you mean by chemical kinetics? So chemical kinetics, it tells you about the rate of the reactions, right? So it is a branch of chemistry which deals with the rate of reactions. Okay, it understands the rate of chemical reactions. So we'll start with the rate of chemical reaction. Okay, so we'll see some definitions of rate of chemical reactions which are involved. So what is a rate of chemical reaction? So it is the change in the concentration of reactants or products per unit time. Okay. So what is rate of chemical reaction? It is nothing but it is a change in concentration of reactants or products per unit time. So how this rate of reaction is given? It is given by decrease in concentration of reactant divided by time taken. Okay, so the rate of reaction is nothing but it is the decrease in concentration of reactant by time taken. So what is the unit of a unit rate? It is mole per liter per second. Okay, so the unit is per mole per liter per second. So what is average rate? Average rate, it is a rate which is measured over a long time interval. So what do you mean by average rate? So average rate means it is average. Okay, so it is a rate which is measured over a long time interval. So these are some definitions. So next is for a reaction. So if you have such reaction, okay, that is X1A plus X2B gives you products Y1C plus Y2D, then average rate of the reaction you write like this. So this is the equation how you write the average. So these represents your concentration. Okay, in bracket what you write, it represents your concentration. Delta T is what? It is change in temperature. Okay, it is change in time. Okay, it is change in time. Small t indicates time. So it tells you about the change in time. So next is what is instantaneous rate? What is instantaneous rate? It is a rate which is measured for an infinitely small interval. So it is for a small interval of time. So instantaneous rate, it is nothing but when you measure the rate at a very small time of interval, then it is called as instantaneous rate. Okay. So what is the nature of reactants? So what type of nature of reactants are used? So first, depending upon the physical rate, okay, physical state, if you have a gaseous state, so what happens to rate of the reaction? So if you have a gaseous state, then what the rate of the reaction will be more. Okay, the rate of reaction will be more. So as you go from a gaseous state, then liquid state, then solid state, what happens to rate of reaction? It goes on decreasing. So rate of reaction goes on decreasing. For gaseous state, the rate of reaction will be more as compared to that of liquid and then compared to that of solid state. So as you go, as you can see this series, so as you go down, what happens? There will be decrease in rate of reaction. Then next factor, nature of reactant depends upon the size of the reactants. Okay. So if the size of the reactant decreases, okay, if the size of the reactant decreases, what will happen to rate? Rate will increase. Okay. So rate, so the size, if the size of the reactant it decreases, what will happen to the rate? Rate will increase. Okay. Then a rate of reaction is maximum in powdered state. Okay, so when you have the rate of reaction is maximum in powdered state, because what happens, there will be increase in the surface area. So whenever you are calculating the rate of reaction, okay, for that is whenever it is in a the substance is in powdered state, so what will happen? It will increase. Why? Because there is increase in the surface area. So next is chemical nature. So nature of reactant, it depends upon the chemical nature. So that is rate of reaction, it increases if the number of bonds broken and formed in the reactions are lesser in number. So it depends upon the chemical nature. That is rate of reaction, it increases, okay, if the number of bonds are broken and formed in the reactions are lesser in number. So the number of bonds which are broken or which are formed in the reactions, if they are less in number, then rate of reaction increases. So this is the third factor which influence your nature of reactants. Then effect of concentration. So okay, what happens to effect of concentration? So you can see the three diagrams. Okay, so if you increase the concentration, what will happen to rate? Rate will increase. So so as you see, if the concentration is increased, so in the third figure you can see the concentration is increased. Okay, there is increase in concentration, the rate of reaction also increases. Okay, so this is the effect of concentration. So we come to a law, that is law of mass action. Okay, so consider a general reaction. Okay, you consider a general reaction. So your A, small a, capital A plus B. Okay, so these A, B, C, D, these are coefficient factors. Okay, they are psychometric coefficient. This capital A, B, C, D, A and B are the reactants, C and D are the products. So A and B reacts to give you the product C and D. So consider this general reaction. So if you write the rate for this equation? Okay, rate is directly proportional to A, that is concentration of A to its psychometric coefficient small a, then concentration of B, okay, and its psychometric coefficient small b. So rate, you give it as small r, so it is directly proportional to your concentration of A and B. Okay, then if you remove this proportionality sign, so this is K is nothing but your constant proportionality. Okay, it is a proportionality sign. So if you remove this proportionality sign, then you have to introduce this small k. Okay, if you remove this, then small k is nothing but your constant of proportionality. Okay, and these small and A and B, okay, these small a and b, they may or may not be equal to x and y. So we'll see this. So rate of reaction, what do you mean by rate constant? Now this rate constant K, that is rate of reaction at unit concentration of reactants, is called as rate constant. So when you have your concentration at unity, okay, if the reactants, the concentration of reactants is raised to unity, okay, then it is said to be a rate constant. That is rate of reaction at unit concentration of reactants is called as a rate constant. So rate law. So if you give the rate law, so the experimentally derived relation of rate with concentration of the reactant. So rate is K into concentration of X into Y. So that is A and B. If you take A or B or X and Y, they may or may not be equal to each other. Okay. So this is a rate law according to the law of mass action. So this is a law of mass action. So based on this, we'll solve some questions now. So the rate of the reaction, okay, the rate of the reaction is expressed in different ways as follows. So this is the rate of the reaction. So you have to write the reaction. How do you write the reaction? Yes. How do you write the reaction? So you go through the option. So the rate of reaction is expressed in different ways. So as follows. Okay. So how do you write the reaction is? So what will be the reaction? How do you write the reaction for this? So this is the rate of reaction given. Then what will be the reaction? So this is the rate of reaction is expressed in different ways. So this is one way. So the reaction, okay, yes, the reaction is B. Okay, the reaction is B. So that is B, okay, B plus 3D, right? 3D here, right? 3D giving you 4A plus 2C. So this is the reaction. So the reaction is B. Okay, so the correct answer is B. So the rate of reaction is expressed in this way. So the reaction of this particular rate of reaction is given as B. The answer is B. The rate of formation of ammonia by the reaction N2 plus 3H2 giving you 2NH3, okay, expressed as derivative of NH3, okay, by dt giving you 2.5 into 10 raised to minus 4 moles per liter, per second. The rate of consumption expressed in terms of H2 as minus d of H2 by dt will be, okay. So rate of consumption in terms of H2. Okay, so for NH3, the value is given as 2.5 into 10 raised to minus 4 mole per liter per second. So what is the rate of consumption for H2? They have asked for H2. What will be the answer? A double, three, B 3 times, C same, D 1.5 time of that expressed in terms of NH3. Yes. Parvati, Rakshita. Yes, the answer is D. Okay. The answer is D. It is 1.5 time of that expressed in terms of NH3. So if you write the rate for this reaction, okay, that is N2 plus 3 NH2 giving you 2 NH3. Okay. So how it will be? We are so they have given it for H2, right? For H2, how you write the rate? 1 by 3 d of H2 by dt, okay, equals to, then for this 1 by 2 d of NH3 by dt, okay. So this 3 goes here, so d H2 by dt gives you 3 by 2 d of NH3 by dt, okay. So it is 1.5 time of that expressed in terms of NH3. Okay, so this is the answer. So the answer is this. Okay, it is D. I hope you have understood it. So we'll go for the next one. So it is 1.5, right? 1.5 the times of H2. Okay, NH3 in terms of 1.5 time of that expressed in terms of NH3. Okay. Consider the reaction 2N2O5 giving you 4 NO2 plus O2. In the reaction, NO2 is being formed at the rate of 0.0125 mole per liter per second. What is the rate of the reaction at this time? So you have to write the rate of the reaction. First step is what? You have to write the rate of the reaction for this particular 2N2O5 giving you 4 NO2 plus O2. You have to write the rate of the reaction for this. Okay. So rate is given as what? Rate is equals to 1 by 4, right? 1 by 4 NO2 by dt. Okay. So rate equals to 1 by 4. What is NO2 value? It is 0.0125. 0.0125 mole per liter per second. Okay. So after solving this, what will get the answer? Yes. Answer, yes. Most of you have answered it as B. So the answer is B. So, so the value of NO2 is given. Okay. So write the rate for this and you have to substitute the value for NO2. You get 0.0031 mole per liter per second. Okay, so this is the answer. It is B. Yes, B is the answer. Yes. So we'll go for the next one. For a reaction, R giving you P. Okay, reactants giving you products. The concentration of reaction changes from 0.05 m to 0.04 m in 30 minutes. What will be the average rate of a reaction in minutes? So now they have asked you the average rate. They have asked you what? They have asked you the average rate. So you have to calculate the average rate. So what will be the answer? How will you calculate that? Yes. How will you calculate this average rate? So average rate, okay, average rate whenever you're calculating, it is, okay, yes. So concentration of reaction changes from, so it is average rate, you're going to find it for the reactant, right? So change in the reactants upon the change in the time, okay? So that is, it is delta, it indicates your difference, it indicates your difference. So it is from 0.05 to 0.04. So 0.05 minus 0.04 is how much? It is 0.01. Okay, that is delta. This is concentration of R, that is reaction. Okay, so into time is what? Time is 30 minutes. Okay, that is 30 minutes. So solve this. Solve this. What answer you'll get? C. Yes, it is C. Okay, it is C. You get 0.00033 m per minute. Okay, so that is 3.3 into 10 raised to minus 4 m per minute. So this is the answer. Okay. So like this, you're going to solve the question. For a reaction, 4NH3 plus 5O2 giving you 4NO plus 6H2O, if the rate of the disappearance of NH3 is 3.6 into 10 raised to minus 3 mole per liter per second, what is the rate of formation of H2O? Okay. So write the rate first. So what is the reaction? 4NH3 plus 5O2 giving you 4NO plus 6H2O. Okay, try to solve this. Yes, try to solve. So 1 by 4, write the rate equation for this. NH3 by dt. Okay, so O2, it will be 0. Then NO will be also 0. Then this will be giving you 1 by 6 d of H2O by dt. Okay. Then what? Just transfer this. Okay, transfer the 6 here. So it will be 6 by 4. What is the value given for NH3? It is 3.6 into 10 raised to minus 3. Okay, equals to d of H2O by dt. You have to find the rate of formation of H2O. Okay, then you have to find the rate for formation of H2O. Okay, so how much it will be? Just see. Yes, what answer you got? It is A. Yes, okay, it is A. So after solving this, you get the rate of formation of H2O. It is 5.4 into 10 raised to minus 3 mole per liter per second. Okay, so this is the answer. Okay, so you have to write the rate of the reaction first, then write the values. Okay, whatever is given and find for the unknown. Okay, like this, you are going to solve the rate. So you, like this, you get the rate of the formation of H2O. Next, we'll see order of reaction. Okay, order of reaction. So here, so the constant A is known as the order of reaction with respect to the reactant A, and B is the order of reaction with respect to B. So you see the equation here. Okay, you see the equation here. Rate is given as, okay, this is proportionality constant. These are the concentration of A and concentration of B. And these A and B, these are nothing but these are the order of reaction. These are called as the order of reaction. So A is with respect with concentration of A, and B is the order of reaction with respect to B. Okay. Then, so the overall rate of reaction, the overall order of reaction is the sum of the exponents. So these are nothing but exponents of all the reactants in the rate expression. So the unit of rate constant is given as mole per liter, okay, raised to 1 minus n and per second. So this is the unit of rate constant. So zero order, so we'll see what are the units, how is the graphical representation, and what are the examples which come under the orders. Okay, so first we'll go to zero order. So the example for zero order is H2 plus Cl2 giving you 2HCl. Okay, this is the first example. Second is 2HI, hydrogen iodide giving you hydrogen. Okay, H2 molecule plus I2. So the rate of zero order is given as proportionality constant K raised to, okay, that is concentration of A into 0 raised to 0. 0 is the order of reaction. So here the graphical representation, how do you represent your graphically is, okay, how do you represent graphically is, that is, this is the, so rate versus concentration of A. You take rate versus concentration of A. It is a straight line. Okay, it is a straight line from this junction. So this is a zero order. So this is a graphical representation. So you have studied this in theoretical part. Just remember, with respect to CET, you remember the graphical representation for each the examples and how the rate is expressed. Okay, so we'll go for the next one. So the rate equation, okay, for the rate equation is given as, okay, concentration of R giving you minus KT plus R naught. Okay, so compare with the straight line, that is Y is equals to MX plus C. So this is a slope. So giving you a slope of minus K. So you write the graph for this particular equation, okay, this equation, and you get this particular graph. Next, half-life of zero order, that is half-life is given as T half is equals to concentration of R naught divided by 2K. So half-life, it is expressed as, you take the graph of T half by R naught. Okay, it is a straight line from origin. It is a straight line. The graphical representation is straight line from origin. So next is first order. The example is 2H2O2 giving you H2O plus O2. Okay, so here the concentration rate is given as K into A. Okay, concentration of A raised to 1. That is the order of reaction is 1 here. Then the graphical representation, you can see this is the graph. Okay, so ln of R giving you, okay, minus KT plus ln of R naught. Okay, so this is the graphical representation for this particular equation. And for log of, when you take log of R naught by R equals to K, okay, divided by 2.303 into T. Okay, then this is your graph. So remember the two graphs. So for both the equation, the graphs are different. Okay, so these are the two graphs with respect to first order. Then half-life of first order. So these are the various graphical representations. Just go through the graphical representation. Okay, so so these are the different graphical representation. So this is a half. So this is a different graphical representation for second order. Okay, these are the graphical order for second order. Okay, so it is from origin. Then this is the half-life of first order. So half-life of first order. So these are the different graphs. So reaction, okay, A giving you product P, order is your 0, then differential form, you write it in this form, okay, d of concentration of A by dt is equals to minus K. Then integrated form is what? Concentration of A is equals to A naught minus KT. Half-life is T half is equals to A naught by 2K. Then reaction, if A is equals, A is giving you the product P, then the first order, it is given as differential of concentration of A by dt is equals to minus K into concentration of A, because first order, it depends upon the concentration, the order is 1. So ln, the integrated form is ln of A equals to ln of A naught minus KT. So T half is equals to 0.693 by K. Then for second order, 2A giving you the product P. Then a differential form is half of differential form of A, of a concentration of A by dt is equals to minus K A raised to 2. The concentration, it is raised to 2 because the order is 2. Then integrated form is 1 by concentration of A giving you 1 by A naught minus KT. Then T half is equals to 1 by K into A naught. Okay, this is the half-life. So this way you give the so we have summarized everything in this particular block. Okay, so just to go through this, it's important. So for first order reaction, if T is 75%, then 2 is you have to multiply it by T half. If T is equals to 87.5%, okay, then T is equals to that is 3 into T half. So we'll solve this question, then you will understand. Okay, so we'll skip this. So remember now what are the key points? In case of gaseous reaction, pressure may be taken in place of concentration. So whenever you have a gaseous reaction, okay, so in place of concentration, pressure will be taken. What is the unit of rate? It is ATM. Okay, that is atmosphere per second. The rate law may not bear simple relationship to the stoichiometric equation. The rate law may not depend on the concentration of every reactant or product of the reaction. So it is not always that the rate law will depend upon the concentration of every reactant or product of the reaction. The rate law may depend on the concentration of species. That is, for example, catalyst. If what are the use of catalyst? They will use or it is used to enhance the rate of the reaction. Okay, so which do not appear in the equation for the overall reaction. So the rate law may depends on certain sometimes on the catalyst also. Okay, these catalysts they will not enhance the they will just enhance the reaction. They will not alter any reactions. Okay, so these are certain key points to remember. What is molecularity? Okay, what do you mean by molecularity? Molecularity of reaction is the number of reactants molecule taking part in single step of the reaction. So for example, so you can see here PCl5, okay, phosphorus pentachloride giving you phosphorus trichloride plus Cl2. This is, it is unimolecular. Okay, it is unimolecular. The molecularity is nothing but it is the number of reactants. Okay, it is the number of reactants which are participating. Okay, taking part in a single step of the reaction. So this is a unimolecular reaction. Then 2 hydrogen iodide giving you H2 plus I2. This is bimolecular. Why? There are 2 molecules of HI, right? So it is called as bimolecular. Then here you can see 2SO2 plus O2. So these are trimolecules, right? The number of reactant molecules involved here are 3. The 2 molecules of SO2 and 1 molecule of O2. So it is a trimolecular. Then next example, NO plus O3. Okay, so these are a bimolecular. NO is 1 molecule, O3, ozone is 1 molecule. So it is a bimolecule. Then 2 carbon monoxide plus O2. So this is a trimolecule. 2 molecules of CO plus 1 molecule of O2. Right. So it is a trimolecular. Okay. Then next is 2 FeCl3 plus SnCl2. This is a trimolecular. So what is molecularity? It is nothing but it is a number of reactants which molecules taking part in a single step of reaction. Okay. So we'll solve some questions. In a first order reaction, the concentration of reactant decreases from 800 mole per dm cube, okay, to 50 mole per dm cube in 2 is to 10 10 raised to 4 second. The rate constant of the reaction in per second is, okay, so try to solve this. So you have to find the rate, okay, rate of the reaction of first order. So use the equation of first order. So I'll give you the equation. So K, small k is equals to 2.303 by T log of A naught by A, right? So solve it. Yes, try to solve this. So your time is what? Your time is 2 into 10 raised to 4 seconds. Okay. Log of A naught. Log of A is what? A naught is 800. Okay. From it decreases from 800 to 50. So A is your 50. This is 2.303. Yes. Solve now. How much you are getting? Yes. First order, right? First order, use a formula for first order and just add the given values and get the answer. Yes. What answer you are getting? Answer me. Yes. Solve it. Take log. So 800 divided by 50. Okay, then whatever you get, take log of that. And then you have to multiply it with this divided product. The answer you get is C. Yes, Rakshita, the answer you get is C. It is 1.386 into 10 raised to minus 4. Okay, solve it and you will get. So first you divide this, then you get something log of. Then this also you get a this. Take a log of this, and then whatever answer you get here, you multiply it with this. Okay, this answer, and then you get your final as this C. Okay, it is C is the answer. For a reaction CH3COCH3 plus I2 in the presence of H plus giving you products, the rate is governed by the expression dx by dt is equals to K into acetone, concentration of acetone into H plus. The order with respect to iodine is, yes, what is the order with respect to iodine here? What is the iodine? What is the, yes, what is the rate order of iodine? What is the order of iodine? Yes, what is the order of iodine? Yes, Rakshita, only one girl is answering. It is 0. Okay, yes, it is 0. So the order is 0. So it is 0. Okay, so the rate, the order with respect to iodine is 0. Okay. The rate of the reaction 2x plus y giving you products is given by. So this is a rate. If x is present in large excess, the order of the reaction is. Yes. So this is the rate of the reaction. If x is present in large excess, then what will happen to the order of reaction? So rate is equals to K into, okay, A square. So the rate will be how many times? So if it will be the rate of the reaction 2x plus y giving you products is given by dy by dt equals to K into x square by y. Okay, that is the concentration of y. If x is present in large excess, okay, and the order of the reaction is, the order of reaction is what? Yes, it is C. Okay, yes, it is C. It is 1. See, the order with respect to x is 0. The order with respect to x is 0 because it is present in large excess. So if it is present in large excess, the order with respect to x will be 0. So the order will be 1. The order will be 1. The conversion of A to B follows second order kinetics. Doubling the concentration of A will increase the rate of the formation of B by a factor of. So the conversion of A to B, okay, A to B, it follows what? It follows second order kinetics. Now doubling the concentration of A. So if you double the concentration of A, okay, if you double, what will happen? Concentration of A will increase and the rate of formation of B by a factor of. So what is done? Rate is equals to K. Okay. So you are doubling the concentration of A. So what will happen? So rate will happen. If you double it, what it will happen? The rate will be 4 times. So it will be 4 times. Okay. It will become 4 times. So rate of formation of B will be 4 times. Okay. It will be 4 times. So the answer is B. Okay. The answer is B. 75% of a first order reaction is completed in 30 minutes. What is the time required for 93.75% of the reaction to be completed? Okay. So we had seen that. So what is it? The time required for 93.75%. Okay. So the time required for 93.75% is given as 2 into, okay, So it is the first order reaction is completed 30. What is the time required for to be completed? So it is given as 2 into T of 75%. Okay. So this is 2 into what is the time required? It is 30 minutes. It is 30 minutes. So how much it is? It is 60. Yes, it is 60. Okay. So like this. So like this, you're going to solve it. Yes, it is A. A is the answer. For the reaction A to B, okay. Skip this. In the first order reaction, the concentration of the reactant decreases from 0.8 molar to 0.4 molar in 15 minutes. The time taken for the concentration to change from 0.1 molar to 0.025 molar is. So in the first order, the concentration of reactant is decreasing from, it is decreasing from 0. Okay, from 0.8 m to 0.4 in 15 minutes, the time taken for concentration to change from 0.1 to 0.25 m is. So you know T half is given here. So right, so T half is given, the value of T half is what? It is 15. So T half is 15 minutes. Okay, because the reactant, the concentration of reactant is changes here. So it is T half, that is 15. Now concentration of 0.1 m to become how much? To become 0.25 m means how many? It will be 2 half lives. Okay, it will be 2 half lives, right? So if you for decrease in concentration from 0.8 to 0.4, T half is 15 minutes. Now for concentration to change from 0.1 to 0.05, it will be 2 half lives. Okay, it will be 2 half lives. So you have to multiply 2 into T half. So it will be how much? 2 into 15. It is 30 minutes. Okay. So for the concentration of reactant to decrease from this, it is T half. So if you want to decrease the concentration again from 0.1 to 0.045, then it will be 2 half lives. Okay, it will take 2 half lives. So you have to multiply it by 2. T half into 2. So you get 30 minutes. So the answer is C. Yes, most of you have answered it C. Yes. Okay. So effect of temperature. So the rate of many reactions are approximately doubled or tripled for every 10-degree rise in temperature. Okay. So what happens with rate of reaction? So as for every change, okay, for every 10-degree rise in temperature, so the rate of reaction is doubled or tripled. So this is the temperature coefficient is given as this. So when the temperature is increased, kinetic energy, what happens to kinetic energy? Kinetic energy also increases. So what happens? The molecules will move faster and there will be more collisions. So more collisions per unit type. So what will happen to the rate? The rate will be fast. So what happens? So as the temperature increases, kinetic energy increases. So molecules moves fast, as well as molecules move fast. What will happen? There will be more collision. So as more collision, what will happen to the rate? Rate will be increased. Okay. So these are. So next we'll see the Arrhenius equation. So Arrhenius equation is given by small k equals to a e raised to minus ea by rt, where k is the rate constant, a is pre-proportional exponential factor, that is frequency factor. Okay, and ea is the activation energy, t is the temperature. So this is Arrhenius equation. So this is the graph. Okay, this is a graph where you are plotting the graph for this equation, log of 10 k equals to minus ea divided by 2.303 rt plus log of 10 into a. So this is the graph. Okay, this is the graph for Arrhenius equation. So activation energy, what do you mean by activation energy? Activation energy is nothing but it is a minimum amount of energy which is required by the reactant molecules. Okay, it is required by the reactant molecules to participate in a reaction. So it is the minimum amount of energy. So activation energy is nothing but threshold energy minus average energy of reactant. So what is threshold energy now? Average energy of reactant plus activation energy. What is activation energy? Is nothing but it is the amount of minimum amount of energy which is required by the reactant molecules to participate in the reaction. So remember what is activation energy, what is threshold energy. Okay. So collision between high energy molecule overcomes the forces of repulsion and brings the formation of an unstable molecule cluster called as the activated complex. So these are the graphs. So for the reaction to progress. Okay. So if the reaction is undergoing an exothermic process, so you can see. So these are the so reactants giving you products. So it will undergo via a activated complex. Okay. So whenever the reactants are forming the product, so it undergoes or it undergoes a collision. So it undergoes a collision between high energy molecules. Okay. So here it undergoes an unstable form, that is an activated complex. So this is the EA. So you can see this is EA energy. Okay, that is energy here, activated and complex. Okay, so whenever you are giving the activated and activation energy, it is nothing but your activated complex minus the ground state. Okay, so this is for exothermic. The first graph, it depicts for exothermic reaction, and this is for endothermic reaction. So delta E, that is energy, change in energy is nothing but activation energy of forward reaction minus activation energy of backward reaction. So these are the two graphs. So we'll solve some questions now. The rate of the chemical reaction becomes double for every 10-degree rise in temperature. If the temperature is raised by 50 degrees Celsius, the rate of reaction increases by about. Yes. So how do you write this? So rate at 50 degree. Okay. And rate at T1 degree Celsius. Okay. So every 10-degree rise, okay, every 10-degree rise of it will be double or triple. So this is what 2 raised to 50 by 10. So it is what 2 raised to 5 times. So it is how many times? It will be 32 times. Okay. So the rate of reaction will be increased by 32 times. So the answer is C. Okay. So rate at 50 degrees Celsius by rate at T1, that is 10. So is given by 2 raised to 50 by 10. So that is a 5. That is, it is the rate of the reaction is increased by 32 times. Okay. In the accompanied diagram, ER, EP, and EX represents the energy of the reactants, products, and activated complex respectively. Which of the following is the activation energy for the backward reaction? Yes, tell this. Which is the following is the activation energy for the backward reaction? It is A. So this is the activated energy. Okay, it is A. Okay, so the activation energy for the backward reaction is given by A, capital A. Okay. The rate constant is given by the equation. This is the equation. Which factor should register a decrease for the reaction to proceed more rapidly? Yes. What happens to energy of activation energy? So this is the given equation. Okay, what happens to energy of activation energy? Yes. So the answer is C. Yes, the answer is C. That is EA. So EA, okay, activation energy. So energy of activation, what happens to energy of activation? Energy of activation, it decreases. It decreases for the reaction. It decreases for the reaction to proceed more rapidly. Okay, it decreases. So which factor? It is minus EA. Okay, that is negative sign, right? So this activation energy decreases for the reaction to proceed more rapidly. Okay, so it is C. The answer is C. The answer is C. Consider an endothermic reaction giving you X, giving you Y with the activation energy EB and EF for the backward and forward reaction respectively. In general, what it is considered for an endothermic reaction. Okay, remember here, for an endothermic reaction, always for endothermic reaction, okay, always EB, yes, EB is less than EF. Okay, so this is forward reaction. Okay, backward reaction is less than forward reaction. So the answer is A. Yes, the answer is A. Plot showing the variation of rate constant with temperature are given below. The plot follows Arrhenius equation is, yes, which is the plot which follows Arrhenius equation? Which is the plot which follows Arrhenius equation? So these are the rate constant and temperature plots. Yes. The plot which follows the Arrhenius equation is, so it follows A. Okay. So the plot which follows Arrhenius equation is A. So this is the plot which follows the Arrhenius equation. For the reaction, the activation energy EA is 0 and the rate constant K is equals to 3.2 into 10 raised to 6 per second at 300 Kelvin. What will be the rate constant at 310 Kelvin? Yes. What will be the, if the activation energy is 0, okay, what will be the rate constant at 310? Yes. See, remember, so if the answer is 0, okay, it is 0. It is 0 because if activation energy is 0, the rate constant will not change in temperature, right? The rate constant will not change in temperature. So it is 0. So what if you change the rate constant also? If you change the temperature also, okay, so the rate constant will remain 0 because activation energy is 0. So the answer is 0. So presence of catalyst. So a positive catalyst always increases the reaction rate by changing the path of reaction and lowering the activation energy. Okay. So always a catalyst, what will happen? It increases the reaction rate. How it increases the reaction rate? By changing the part of the reaction. And whenever there is a catalyst, it will lower the activation energy. So by changing the path of reaction and by lowering the activation energy. So presence of catalyst plays a very important role. So collision theory. So for a bimolecular elementary reaction, A plus B giving you products, that is Z. Okay, Z is nothing but your collision frequency. Collision frequency of AB represents the collision frequency of reactants A and B. So a chemical reaction takes place due to collision among the reactant molecules. So what is this collision frequency? The number of collisions which are taking place per second per unit volume of the mixture is known as the collision frequency. What is collision frequency? It is a number of collisions. Okay, it is a number of collisions which are taking place per second per unit volume of the mixture. It is known as the collision frequency. So every collision is not effective. For the collision to be effective, the molecule must be properly oriented in space. Okay. So to account the effective collision, another factor P, that is probability factor, is introduced. So this is P is nothing but your orientation factor or probability factor. So in collision theory, so this is the equation. If you introduce the probability constant or probability factor, in collision theory, activation energy and proper orientation of the molecules determine the criteria for an effective collision and hence the rate of the reaction. Okay, so So whenever you're considering the collision theory, this activation energy, okay, EA, activation energy EA, and your proper orientation, that is P. So these determine the criteria for the effective collision, and hence it tells you about the rate of the reaction. So which one of the following is not correct? Yes, which one of the following is not correct? Go through the options. Which one of the following is not correct? Yes, which one of the following? Every biomolecular collision does not result into chemical reaction. Collision theory is not applicable to unimolecular reaction. Collision theory assumes molecules to be hard sphere, all the above. Okay, the answer is B. Collision theory is not applicable to unimolecular reaction is a wrong statement. So it is B. Okay, the answer is B. Next, when a catalyst increases the rate of reaction, the rate constant, what happens to rate constant? If the catalyst, it increases the rate of reaction, what will happen to the rate constant? Rate constant also, yes, it increases. Yes, rate constant also increases. So in the presence of catalyst, activation energy, what happens to activation energy? It decreases. Hence, the rate constant will increase. Okay. So whenever you have a catalyst, activation energy decreases, rate constant will increase. So the answer is B. Yes. Which of the following statement is correct? Okay, just go through the statement and tell me which one of the following statement is correct. Yes, all are correct. Yes, D, all are correct. So catalyst is used in rate determining and formed again. Okay, the catalyst does not appear in the overall equation for the reaction. The role of the catalyst is to provide an alternate activated complex, one with lowered activation energy. So the answer is 3, D. So all the statements are correct. Okay. So the reactions of higher order are rare because why the reactions of higher order are rare? Yes, the reactions of higher order are rare. Why? Yes, many body collisions have a low probability energy. Okay, so many body collisions have a low this. Okay. According to collision theory of reaction rates, the rate of reaction depends. The rate of reaction depends. Yes. On what does the rate of reaction depends? Rate of reaction depends on what? It depends only on the colliding molecules with energy greater than threshold energy, and it depends upon the orientation of molecules at the time of collision. Yes, it depends upon B and C. Okay, it depends upon B and C. So collision theory depends upon colliding molecules with energy greater than threshold energy, and it depends upon the orientation. It depends upon the orientation of molecules at the time of collision. So it is D. Okay. So we'll solve, we'll solve some questions. So take down, so the question is the time required, okay, the time required for 60% completion, 60% completion of a first order reaction, is 50 minutes. Okay. The time required for 93.6% completion, okay, of the same reaction will be A 50 minutes, A 50 minutes, B 150 minutes, C 100 minutes, D 83.8 minutes. Yes. Yes. How you will solve this? How you will solve this? What is the answer? See, for the first order reaction, okay, for the first order reaction, the rate constant is given as a what? K is equals to 2.303 by K, okay, log of R naught by R, right? Right. Then what? So what they have given at 50%, okay, at 50%, sorry, at 50 minutes, right? The time required for 60% completion of a first order reaction is 50 minutes. So give so 50 minutes. So what is time? So at 50 minutes, okay, 60% of reaction is completed, right? Reaction is completed. So this is given for us. This is given for us, right? So what will happen to K now? K is equals to 2.303 by T. Okay, 2.303 by T. Okay, then log of what? Log of R naught by R. So here what is 2.303 by T is what? Our T is given as 50 minutes. 50 minutes, right? Then log of what 50%, 60% work is done. So it is 100 minus 60. 100 minus 60 is what? 40. Right. So after solving this, you get what? So you get 2.303 by 50 into log of 40 by this is 0.397. So the answer will come to this. Okay. So this is okay. Then after this, so what they have done, this is for our, this is time required for 60% of work completion. Now they have asked what is the time required for 93.6%. Okay. So for 93.6% of reaction is completed. Okay. When 90% of reaction is completed, so it is 2.303 divided by 50 into 0.397. Okay, this, okay, 0.397 equals to 2.303 by T log of, right, how much? 93.6. So 100 minus 93.6 is what? 100 divided by 6.4. Okay. So after solving this, 2.303 by 50 into 0.397, okay, equals to 2.303 by T into log of this 100 divided by 6.4. Okay, if you would take log of that, it will come to 1.19. So after solving this, okay, your time, you're finding out time. So time will come to approx 150. Okay, it comes to 150. So the answer is B. So the answer is B. Okay. So the answer is B. I hope you have understood. One more question will solve. What is it? The plot of T half. Okay, the plot of T half versus R naught for a reaction is straight line. So it is a straight line parallel to the x-axis. The unit for the rate constant of the reaction is. So you know this is T half by R naught. Okay, R naught. So the plot of T half versus R naught is a straight line parallel to x-axis. The unit of rate constant for this reaction is, what is the options are mole per liter per second, B mole per not per second, this is only second, then C per second, D liter per mole per second. Yes. What is the answer? What is the T half? So you know T half is what? The answer is C. Okay, the answer is C. because T half is independent of initial concentration. It is independent of initial concentration of the reactant in the first order. So this is first order, so it is independent. So the rate, the unit for the rate, this will be per second. Okay, it will be per second. So I hope you have understood today's session. So we'll stop it for today. Okay, and we'll continue with the next chapter in the next class. Thank you. Have a nice day.